Hello? Today I'd like to talk about trusses and how the loads are flowing through the elements of a truss depending on the hinge conditions. We have seen trusses in many instances as engineers or engineering students, obviously, and we always assume the joints for these structures will not carry any moments, shears, etc. That is our assumption. And I'd like to show you whether or not this assumption is all that significant. And you will see at the end of this demonstration that it may not be as significant as you might have initially assumed. So I'm creating a truss here with a pin and a roll connection on both ends. I have two cords, one at the top and one at the bottom. I am now bracing them with these brace elements, and here's my truss. My truss is complete. Now I want to load my nodes right here along this cord with some forces, concentrated forces, pointing down as the gravity loads, and I have loaded my structure. And obviously it led to some axial forces, and you can see that we have compression indicated by red at the top cord and tension at the bottom cord, as we would predict. And this would be, it would deflect, as you can see here in this animation, and this is our truss. Now, the question is, of course, we have loaded our structure. I chose 5 kilonewton at every joint and ended up with these reactions on both sides. Now, the question is, this structure obviously assumes that everything is connected to each other with perfectly fixed connections. With the exception of the supports, they allow rotations, and this roller also allows sliding motion. But ultimately, everything is connected together monolithically. That's the assumption. Well, that leads to, obviously, some moments forming within the structure. But when we design trusses, we do not assume moments existing in our truss. Now, I'm here to show you that this assumption is a very good assumption, and it actually works whether or not we include hinges within our structure or not. I'll demonstrate by copying the structure and creating another one just like that. And you'll see the loading conditions are the same, the structure is the same. I'm going to add hinges to the beginning and end of all braces, and also every section of the cord. As such, I will skip these two elements, because if I add that, then I will have 3 hinges on all. That would be a mechanism, but you'll see that by doing this modification, even though it still has this similar axial loads, same loading conditions, it has no moments, now no curvatures, no shears, none of that. But if you look at the axial forces, you see something very, very similar. And the distribution of the load is also pretty similar. That's external stability, but you will see even the internal forces will be very, very similar. But before I start comparing these two and the numerical values of their axial forces, I'd like to copy another one and I show you what would be a more realistic truss made by an engineer. Usually, in an engineering structure, you're not going to have hinges on every joint of the cords. The cords will probably just run longitudinally, because you will have a long cord that you can just utilize, and you will end up using it as such. And I have removed, therefore, all of the cords out of this, all of the hinges in the cords. Now, you may end up having a cord that is a little too long. If you need a splice, you end up usually adding that in the middle of a cord somewhere where the complexity of these joints are sort of skipped, and you can have a hinge in the middle. If you compare the moments, you'll see that moment diagram for this element, this realistic truss, and this perfectly fixed truss are comparable. Of course, the ideal truss doesn't have any moments in them, and you may think, well, let's go ahead and compare the axial forces. Now look at the values of the axial forces. You have 22.46 kilonewton here, with some more digits if I click on them, and you'll see they are very, very close. 22.28, 22.50, 22.46. And look at these braces at the end, 17.44, 17.67, 17.45. These numbers are so close that if you look at it from an engineering perspective, you'll realize they're practically the same for all engineering purposes. So the axial forces are the same. The moments are different. You'll see some moments here, and they're not perfectly in agreement. Obviously, the ideal truss has nothing, but I'll show you that in reality, these loads are very, very small for a truss, for an element that is spanning across this whole distance. How do I show you that? I can demonstrate this by copying just the bottom chord of one of the trusses, and I'm going to use that to demonstrate to you that, let's switch to a little bit of a beefier section here, and you'll see now this is an element that works in bending, right? We'll have a lot of shear. Look at all the shears that we had. They have become in values also very, very small in comparison. Look, 12.5 kilonewton, while on these elements you have everything represented by just newtons. Very, very small, not even the same order of magnitude. And you can tell that by just looking at the visuals of these. And look at the moments. We have an element now that has some real moment on it, right? We can actually look at the values. 22.5 kilonewton meter. For this whole span, if you're working under bending, you have about 22.5 kilonewton meters of moment. But look at the moments here. These are 61.95 newton meter. It's not even in the same order of magnitude. So in reality, yes, you will have some moment on your elements, but on your truss elements, if you do not add those hinges to your structure, but they're not going to be as significant. Why is this? Why do we have such a thing? Why do we have our trusses sort of immune to all of these hinges, and their behavior doesn't change as much depending on the hinges? And that's because mainly due to the fact that all of these links, we have the cord elements and the brace elements, they're all a lot stiffer axially than they are in bending. Therefore, by using the truss geometry, using these triangular shapes, we are making use of a different mode of work. Look at the normal forces. For this girder, we have none. We have all normal forces within these frames. And basically, we are changing the mode of working for each element. Now, these top and bottom chords work together to handle the moment, forming a couple. And then these braces diagonally work to create and handle the shear. So everything works axially, but they still overcome the same loads and same forces, because ultimately the goal is to span this distance carrying all 5 of these loads and move the force to the supports. That's the goal of our structure. And you will see that this is achieved for the trusses axially, while in the girder it is achieved in a bending mode. I would advise you to try and imitate and simulate the actual behavior of your structure. So you will probably be better off by a structure like this. Wherever you actually have those simple connections, use your hinges, know that you're not going to be transferring any moment there, and simulate your structure accordingly. But I'm just here to tell you that ultimately these choices make very little difference in a truss. So they may not matter as much as you would normally assume. So this is the insight that I would like to share with you in this video. Thank you very much. I appreciate it.